all yours.
Great, thank you. I noticed somebody dropped these off. Wasn't me.
I think those are for all of us to use.
Yeah, but they're tropical. So today I'm going to talk about the discrete case of tropical geometry. Set me up, right? First, like last time, let's just quickly review the end of last lecture. So Stoll's bound was similar to Coleman's, so still a prime of good reduction, but the bound is 2r instead of 2g minus 2. A review of Coleman's method, so this kind of summarizes what goes on. In this analysis, you work residue class by residue class, and then in each residue class, you can show a local bound. This is kind of a Rawls theorem. So the sum of 1 gives you number of FP points. And then Stoll's idea was to, for this NQ, instead of picking a single differential, to pick the best differential among the annihilating differentials. So meaning the differential with the minimal evaluation at Q, or its reduction at least, or equivalently, the minimal number with multiplicity of zeros in the residue disk of Q. And then he set up this divisor, which I call the Chabauty divisor, and bounding the degree. So this part's just formal. Bounding the degree is the same as bounding these NQs. So just the slides directly from last time. And instead of Riemann-Roch, we get to use a different kind of global theorem from the geometry of curves, which is Clifford. So what Stoll shows, so this is the same D, and the claim is that this D is special. This H naught of omega twisted by minus D, section of this is the same as a holomorphic differential, but where D appears as part of the support of div of omega. So this will generally cut down. I mean, each point on D will cut down a bit on the dimension of this. And essentially, by the definition of these NQs in D, every annihilating differential is an element of this twisted space. So this had dimension G minus R. So this has dimension at least G minus R. And by Clifford's theorem, this space has dimension at most. Okay, so this has 2G plus 2, or minus 2. And this is minus, what's a typo? Minus degree of D. And so if you just clear everything, you get Stoll's theorem. So that's a review, and I want to rephrase Stoll's theorem slightly, almost imperceptibly at first. And talk about slide 1, ranks and linear series. So just recall that for a divisor D on a smooth proper curve, that the linear system is simply the set of effective divisors which are linearly equivalent to D, and that this is isomorphic to some projective space. Well, the projective space is proj of just H naught of D. And less familiar, maybe, is the notion of rank. So let's just formally define the rank of a divisor to be minus 1 if the linear system is empty. So meaning, if D is not effective, that was not part of the linear system definition, if D is not effective and not equivalent to an effective divisor, we say it has, well, minus 1, or if you like, minus infinity is fine. We say that it's at least 0 if D is equivalent to some effective divisor. Okay, we'll say it's at least 1 if, okay. So here's the idea of the rank. I'm going to play this game. Maybe D is effective to start out. I'm going to play the game where I want to make D non-effective and keep U from being able to fix whatever damage I've done. So to make D non-effective, I'm going to remove a point for it. So for every point P, so I really mean closed point, the linear system D minus P is non-empty. So again, the way you should think about this is I can do 1 point of damage to D, but you can heal that, you can fix that. And then in general, the rank of D is at least I if for every I many points of damage. So effective divisor of degree I, maybe I'll say greater than or equal, no, less than or equal to I, D minus E is non-empty. So this is like saying if I put I many negative points, or add I many negative points to our divisor, there's still some linearly equivalent divisor. And at first, this seems like a lot of work for nothing, because if X is smooth, then the rank of D is the dimension of H naught of X D minus 1. And I claim this is pretty clear. So somehow this condition of D minus a point, H naught of D minus P, its dimension can only differ from the dimension of H naught of D by at most 1. It might be the same, that can happen, but it can only decrease by 1. And so the dimension of this, you should think of these as the maximal number, this rank is the maximal number of linearly independent conditions you can impose on the divisor D. On the other hand, as I discussed last time at the end, if X is singular, then, well, these H naught spaces are weird, so the ranks are not equal. Maybe not equal to the dimension. Simply because even on something like the coordinate axes, functions could, maybe if this is your divisor, maybe every function either vanishes along this or vanishes along this. And then right, so why bother? Why bother is here. Really, in the Schill's proof from before, what we're showing is that the rank of K minus D, so omega 1 of minus D, is at least G minus R. And we can reformulate this proof in place of ranks. So we'll do that in a second. But quick couple of digressions. One comment about this rank is that it specializes. So 2, rank of D is upper or lower. It's semi-continuous. Meaning, if I have a model, say over a DVR like ZP, so that the generic fiber specializes to the special fiber, and if I have some divisor P, Q, maybe P prime, Q prime, so I'll just call this D and D prime, then the rank of D can only grow. So technically this is Hartshorne chapter 3, section 12. That's overkill, that's cohomology and base change. These are just H naughts, it's fairly explicit. You can work it out by hand, but it's technically a special case. And I'll comment that this can be strict. So for instance, okay, the following is not obvious, but you can have a non-hyperelliptic curve degenerate to a hyperelliptic curve without introducing any singularities. And so in that case, if you have P, Q, and X not hyper reducing to, let's just say P prime and Q prime, but where Q prime is the image of P prime under hyperelliptic involution, then H naught of P plus Q is 1, and H naught of P prime plus iota P prime is 2. So in general, this is not strict. kind of a feature. So one quick technical definition. That we need, and then we'll get back to divisors. Let X be a scheme. And we say X is regular if for every point of X, let's just say this corresponds to some ideal script P, the dimension of P mod P squared is a K of P vector space, so it's the residue field, is the same as the dimension of X. So this is the Zureick tangent space, and this is just saying that the dimension of the tangent space at every point is the same as the dimension of the scheme. Smoothness is a relative concept. This is an absolute concept. So this makes sense for something like spec of Z, spec of O of K. And what? Great. Just as a quick example, if I take something like y squared minus x cubed minus p, but over zp, so x to spec of zp, this morphism is not smooth, but x itself is regular. If you don't like zp, you can do the same example over C adjoin T, but where P is T. Then it's like saying the total space of A2 is smooth, but the fibers are singular. This is regular. Here's the model. X is two-dimensional. On this fiber, there's a singular point, 0, 0. The corresponding maximal ideal is x, y, p. And then m mod m squared is generated by x, y, and p, but it's actually only generated by x and y. Because of the defining equation, p is in m squared. Here it is as an element of m squared. On the other hand, if you put some power of p, then this part fails, and x is no longer regular. So instead of in terms of the tangent spaces and ideals, you can also understand regularity in terms of the local equations. So once again, why bother? So if x over zp is a regular, so now we know what that means, proper model of a smooth curve. So what I mean is the generic fiber is a nice curve. The special fiber, mod p, might be singular, like in this example, but at least the total space is regular. Here is why the adjective regular comes up so frequently in arithmetic geometry. I mean, it's also a natural notion, which is that if I take the image of the map from x qp to x of fp, so this is the reduction map. Everything is proper. I mean, also implicitly, I want this to be a flat model, not, but it's a model of its generic fiber. So the reduction map, okay, in this case, things are projective. The reduction map is scale the coordinates of your point until you can reduce to something which is a point of x of fp. But it's also proper, so I'm using the evaluative criterion of properness, and the point is this is contained in the smooth locus of fp. So as an example, back to y squared minus P, if I take the point, so the singular point on the special fiber, 0, 0, and I look at the tube, meaning the set of QP points which reduce to 0, 0, you can see essentially by elementary number theory that there are no QP points which reduce to 0, 0 by looking at valuations. So this is empty. I mean, as a rigid space, it's not empty. It just has no QP points. On the other hand, if I take the same equation and write down a non-regular model, then the tube contains the point 0p. So we discussed in the first lecture, at least the statement Lorenzini-Tucker, and then there's an alternative proof by McCallum and Poonen. So same hypotheses as usual, except instead of a prime of good reduction, we have a regular proper model. And their statement was that x of q has at most, so I'll write x smooth of fp plus the Riemann-Roch term. And so when I write x smooth, what I really mean is, okay, it's a curve over spec of zp. It has, the special fiber has some singular points, just remove those. And this fact about the image of the reduction map tells us that we really have the same, so in Lorenzini-Tucker at least, proof, but which is now, if our model is something like this, then any rational point, okay, by star, reduces to a smooth point of the special fiber. And then conversely, if I have some q, the tube of q is still isomorphic to PZP. If I take the cube of a non-singular point, then it might be an annulus, it might be something more complicated, but we didn't really use, or one doesn't really use in the proof of this isomorphism that X is smooth, just that it's the residue tube of a smooth point. And so in the proof from before, basically take, the point is you work residue disk by residue disk, or rather in the proof from the very beginning, you're considering the integrals just in tubes over smooth points of the special fiber. So Riemann-Roch on the special fiber is trickier. There's still a notion of this. You can see, for instance, Qinglu's book on arithmetic and algebraic geometry. But Lorenzini and Tucker really figure out a way to use Riemann-Roch on the generic fiber instead of the special fiber. And a lot of the work is showing that Chabauty's setup works in the bad reduction case. There are issues that we'll discuss next time. And then McPoonen shows, they give an alternative proof in their survey in the appendix using, instead of Riemann-Roch, using arithmetic intersection theory and adjunction on the model. So next, our idea, or rather, my idea as a graduate student was to take the fiber product of all of these proofs, and the thing that goes wrong is this notion of rank. And Stoll's proof does not specialize well for singular curves. So let's talk about the discrete case of tropical geometry. So Matt Baker in Barbados explained to me the following idea, which is that we were not being degenerate enough. So degenerate even more. Throw away the geometry and just work with the combinatorics of the special fiber. So if you have a stick figure, so in this case just, a stable curve, a bunch of P1s intersecting transversely. then you can associate to this its dual graph. So for each component, you associate a vertex, and then for each intersection, you add an edge. So this dual graph would be, so we have left, right, top, middle, bottom, left connects, right connects. And you can see the genus of the arithmetic genus of the special fiber is the same as the genus, or anybody in combinatorics objects to calling it genus. Anybody in geometry is fine. The first Betti number of this graph. But a little better is Matt realized that you can also degenerate divisors. So if I have a divisor, for now at least supported on the smooth locus, so maybe I'll put 1, 1, 1, minus 1, and call this D. We'll call this of D. And the idea is, so you no longer distinguish between individual points. I mean, you're on a P1 anyway, at least in this case, and you just count how many points are on each component. So top, 1, did I do that? Nope, I already did that wrong. Yeah, this one's 1. This one's -1, 0, 0. The divisor has the same degree. Well, what is the degree? It's the sum of the numbers. Formally, okay, so we call this div of gamma, an analogy with the geometry of curves. And formally, this is just the free abelian group on the vertices of gamma. So in Matt's series of papers, which have various co-authors, but the ones I need here, so Baker, and then Baker, Noreen. So Sergei Noreen was a combinatorics postdoc at Georgia Tech. Workout, and I'll spend the rest of the lecture explaining this and explaining how it connects to number theory and geometry. So Matt has a notion of linear system, so in particular equivalence of divisors, and a notion of rank. This notion of rank is semi-continuous, so the rank of D on the geometry side can only grow when you specialize. There's a notion of canonical divisor, K gamma, actually just formally, but I'll motivate where this comes from. It's very clear. This is, so at each vertex you have a degree, the number of outgoing edges, and you put the degree of V minus 2. So here, instead of writing it as an element of Z, I'm writing it like a divisor. So I mean, at the vertex V, you put this number. So on this graph, the canonical divisor would be, these have degree 2, so you would get 1, 1, 0, 0, 0. The 2G minus 2 formula for genus still holds. And where did I go? Okay, great. So there's canonical divisor, notion of special, and then still theorems of Riemann-Roch and Clifford. But generalized, let me start a new page. Of course, these linear systems are not projective spaces. These are going to be finite, as we'll see. And there's no vector space that you can take, or thing you can take the dimension of H naught of in this picture. So nonetheless, so for Riemann-Roch, Baker, and Noreen, you can just rephrase it in terms of ranks. Even though there's a -1 when you compare with H naught, there are 2 -1s. Gamma D is the degree plus 1 minus G. And then Clifford is, if D is special, then the rank of D is at most the degree over 2. Okay, so I'll justify and motivate these theorems, but first let me show you how, at least in this very special case, this fixes our fiber product of proofs. So with cats, let's add a hypothesis just to make it reasonable to talk about in public. So suppose we have running hypotheses, so it's still R less than G, regular proper model, and assume that the special fiber, as I said, get more degenerate. Let's get totally degenerate. So such a curve is an isolated space on the moduli space of curves. It's just a stick figure. It's a bunch of P1s meeting transversely. You can't degenerate it any further. If you like, this is a Mumford curve. Our proof is more general, but in the totally degenerate case, we only need Matt Baker's theory of specialization. And the main content of our paper is to figure out how to replace what Matt and others did in the case when the components are not P1s. So how to incorporate both the combinatorics of the special fiber and the genera of the different components. But for this lecture, let's talk about just the most discrete case. So we show two things. Then we show that the specialization of this Chabauty divisor, so where this D shub is the sum of NQQs from the proof, we show that this is special. Okay, good. And actually, we show that the rank of K gamma, okay, so remember gamma is the dual graph of the special fiber. So it's not just special, it has the same lower bound from Stoll's proof. It's at least G minus R minus 1. So how do these two well, no, first of all, one more time, recall that the problem was on X sub FP, the Chabauty divisor was not special. There's this problem again of functions or sections of line bundles can identically vanish along components, but somehow you skip that step and specialize further to the dual graph, and it becomes special again. So the most technical part of our paper is actually showing the G minus R minus 1 rigorously. And then just quickly to finish, the proof of rank favorability is essentially the same. So we have the rank of K gamma minus sp of D is, on the one hand, at least G minus R minus 1, and on the other is at most the degree of this gamma minus, well, the degree of sp D is the degree of D. This is what we're trying to bound in the proof over 2, and it's really the same proof. Plus the degree of D. So you just collect. Okay, so I hope I've sufficiently motivated for you what we're about to do, which is to draw pictures of graphs. So what is the notion of rank? What is the notion of equivalence in linear systems? So the following predates Matt Baker. Matt started thinking about what I'm about to explain, chip firing, because he realized that this connected to geometry of curves and number theory. So if you take a finite graph and you have a divisor on this graph, so 1, 0, 1, minus 1. So Matt has a survey which is called the dollar game, or the dollar game on graphs. Some people call this chip firing or sand piles or critical group. So you should think of a divisor. You have an integer on each vertex, as a collection of money. Each vertex has either some money or some debt, and the goal is to get out of debt. And the way you can do this is or get everybody out of debt. And the way you can do this is by lending or borrowing. So if this vertex wants to lend money or borrow money, he can only do it in an egalitarian way. He has to borrow the same amount of money from each neighbor. So if this vertex borrows, he borrows one chip from here and one chip from here. So this becomes equivalent to nothing, 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 and 1. We're out of debt, and this is winnable. If you prefer, you're trying to make the divisor effective. So similarly, if I take something like 1 minus 1, 0, so this has degree 0. If we can make it winnable, nobody has any money. So this guy can be greedy and borrow this vertex. So he'll borrow 2. This will be left with 0, and this will be left with minus 1. So you can see kind of by symmetry, for this divisor, any amount of borrowing is just going to run you in circles, and you can never get out of debt. Whereas if I take something like this, 0, 3, minus 3, well, a good Samaritan can lend, and this becomes 1, so he lended 1 in each direction, 1 minus 2, and this vertex sees an opportunity and borrows. That's 0, 0, 0. And it's not a coincidence that there are 3 edges and there is a 3 there. So this gives you a notion of linear equivalence. So we say that D is equivalent to D prime if they differ by some necessarily finite sequence of lends and borrows. And once you have a notion of equivalence, you can, at least formally, set up all of the same definitions from the geometry of curves. So, for instance, we'll define pic of gamma to just be div of gamma mod this equivalence. So these are the same element of pic of gamma. These are different elements of pic of gamma. These divisors have a notion of degree, and notice that when you borrow or lend, you never change the total amount of money in the system. So there's a notion of pic not of gamma. Not totally obvious, but pic not of gamma is finite. Really, the easiest way to provably do these computations is to set things up in terms of adjacency and Laplacian matrices and do a little bit of integer linear algebra. There's a bunch of linear inequalities that these satisfy when you write out equations, but this pic not is finite. Just as a teaser, this group actually comes up in the neuron models book. This happens to be isomorphic when you're degenerating to the component group of the special fiber of the neuron model. I think I got that the wrong direction. So, touch my face. So, and then even crazier, if you haven't thought about these things, this pic not is its order has a pretty formula, which is it's the number of spanning trees of the graph, which is weird because there's no natural group structure on the set of spanning trees. Maybe there's a spanning tree torser. The proof of that, though, is just when you write this out in terms of matrices, the order of this group it follows from the matrix tree theorem. It's the product of some number of eigenvalues. So, similarly, you can set up a linear system. This is just the collection of D prime, which are out of debt, effective, such that D prime is equivalent to D. Again, this is finite, not totally obvious, but here's a hint. If everybody borrows once, nothing happens because you're sending the same amount of money in and out. And so when you start working with this, you quickly can kind of set up some polytope and look at integer points, or in that polytope, or lattice points rather. And then the rank is the same definition. So the rank is at least I if for every effective E with degree at most I, D minus E is non-empty. So to put it another way, you have some community, so some divisor that is possibly out of debt, and somebody adds some small amount of debt to the community, and you ask, how much debt can the community handle? Can you get it out of debt? How much damage can you do to the divisor? So just like examples, if I take this divisor, the rank is at least 0 because it's already effective, and I claim the rank is exactly 0. So if I were to remove a chip here, it would already be effective, no equivalence necessary. And then if I were to remove a chip here or here, we'd have one of these examples. On the other hand, the rank of something like 1, 1, 0, I claim is 1. Again, if I remove a chip here or here, then it's already effective. And if I remove a chip here, I can always lend. So it can handle one extra piece of debt. But if I were to remove 2 chips here, okay, so let me just say this is fine. This is equivalent to 0, 0, 2. Nope. This can borrow. This is equivalent to 1, 0, 0, but if I take 0, 1, if I remove 2 here, this has empty linear system. And by the way, these theorems like Riemann-Roch and Clifford, so Riemann-Roch tells you that if the degree of D is large enough, then you can always get out of debt. And quantifying how large is what Riemann-Roch tells you. Okay, so that is the notion of linear system rank that we use in this proof. And in the remaining 13 minutes, I want to explain why this comes up in geometry. So if I have a model of a curve with special fiber, the union, so I'm just going to label them CI. So if the special fiber looks like this, C1, C2, etc., genus 2. Then these are out of order. 1 second. Oh, this is fine. So it's a lot cleaner if you work with line bundles than divisors. So I claim there's a map from PIC of the model. So when we're working with curves, the model is 2-dimensional. That's fine. Specialization to div of the dual graph, which is if I take a line bundle on Eeks, its specialization I define to be the following divisor. So I need to give you, for each vertex of the dual graph, an integer. And the vertices correspond to the components of the special fiber. So I can restrict L to the ith component. This is now a line bundle on a curve. In fact, in this case, it's a line bundle on a P1. But this specialization works even if the components have genus. And I can take the degree of this. If you like, every L is of the form O of D for some D. Take the degree of that divisor D, or pick a section of L and take degree of div. And then I'll put this integer at the vertex VI corresponding to C. And this will be my divisor. And did not leave enough room for the example. Which, by the way, there's a funny feature. I really do want isomorphism classes of line bundles here, but no equivalence here. It's weird that an isomorphism class gives you just a divisor, not up to equivalence. But that's a feature, as we'll see. So let's do 2 examples. let's take L to be O of Ci. So remember, for a divisor D on a curve, or a divisor D on a variety, O of minus D is the ideal sheaf, and then O of D is the dual. Sections of this are functions where they're allowed to have poles. It's C. In any case, and then keep in mind, this is two-dimensional. Eeks is two-dimensional, so a component of the special fiber is one-dimensional and is a divisor. So this curve is a divisor. And so let's calculate, if I take O of Ci and restrict to Cj, that's what we need to do to specialize. Okay, there are two cases. I'll go first. If I is not equal to j, and this is just the number of intersection points. So of Ci intersect. Okay, I could have just written that. So if I is not j, boom. And then if I is equal to j, so now we're on to chapter 5 of Hartshorne, this computes the self-intersection of C. Of C. It's really the normal bundle. To explain quickly, so I said that a component of the special fiber is a divisor. Of course, the special fiber is also a divisor, but its principle, so notice that Eeks FP is just the divisor of our uniformizer. So in particular, the sum of the CIs is equivalent to 0. So Ci is equivalent to minus sum of Cj, j, not equal to I. And I want, I meant degree here, because if I don't, that's just a sheaf. So the self-intersection of Ci is really minus, this is minus the number of intersection points of Ci with the rest of Eeks. So just to be really clear, in this case for C, let's call this C1, if I were to specialize O of C1, then I would get, so C1 is, let's color it more, it's this. It intersects with the rest of the graph at 3 points. So I would get 1, 1, I drew the graph wrong, didn't I? Great. I would get 1, 1, 1, and then minus 3. So we just saw this divisor. This divisor is the effect on the graph of firing at the vertex 1. So, okay, this is the key to everything. Restricting O of C is the same, so of O of Ci has the same effect as firing at vertex I. So that's suspicious. Let's do a second example. So I only know about 2 sheaves, so these O of Ci's, and then the canonical sheaf. So 12. If I take L is omega Eeks, then we can compute with a junction. So we really want to compute omega restricted to Ci. A junction gives us a formula for omega Eeks tensored with O of Ci restricted to Ci is omega 1 Ci. And then in this case, the Ci is a P1, so this part has degree minus 2. So in particular, omega, the degree of this is the degree, okay, it's minus 2, minus the degree, which is minus 2 minus, or no, plus now, the number of intersection So we just calculated this. Points of CI with the rest of X. So to put it another way, this is the canonical divisor on the graph. The number of points concentrated at vertex I is the degree of CI minus 2. So what's the upshot? Okay, so let's draw a picture. So suppose I have some divisor on this special fiber, and I specialize it. So I just reduce. And then, so I'll call this D. And suppose I have a different divisor, which is equivalent D prime. So we have two divisors, and we have an equivalence D prime on the generic fiber. Well, this equivalence is given by there's some f such that div of f is D minus D prime. And if we extend f to the full model, so here lowercase f is a map from X QP to P1. If we extend it to the full model, let's call this capital F, and let's call these closures D bar and D prime bar, then div of capital F is D bar minus D bar prime, except that this function f can now have zeros and poles along components. Maybe it vanishes identically here. Remember, this was the problem with Clifford's theorem, special divisors, et cetera, on singular curves. So it could have a pole here, and then maybe so a pole here, and maybe a identical zero here. So you get an extra term, which is plus some AI of what we call vertical divisors. So here's the neat thing. This was a problem when we were working with divisors on the singular curve, but it becomes useful when we think about divisors on the dual graph. So this divisor D bar, okay, it specializes to the dual graph. You just collect where the blue points land. Or if you like line bundles, you take O of D bar. And the upshot is that the equivalence in the chip firing sense of D bar with SPA of D prime bar is witnessed by lending, okay, so the negative of lending is borrowing, lending at CI, okay, or rather vertex I, AI many times. So I'll repeat this. These multiplicities of vanishing along components of the special fiber give you the recipe for how many times to fire and where to take the specialization of this divisor to the specialization of that. So great. This, by the way, proves, or at least if you figure out how to deal with algebra, extensions, I've kind of only really been working over QP on the curve side. This really proves Baker's specialization theorem, simply because, okay, look, if you remove some point from D, make it equivalent to D prime, on the generic fiber, if you have enough rank to find an equivalent effective divisor, when you work on the model and specialize, the components which appear as vanishing in poles of your F tell you how to do the same equivalence combinatorially. And of course, if you want a proof of this, just take O of this equation. O of d bar is isomorphic to O of d bar prime plus this. Okay, so this is the key to all of the connections. And in minus 30 seconds, I just want to say, you have the same picture for line bundles. If you have a section of a line bundle, like canonical, well, div of that section gives you a particular canonical divisor on the generic fiber. If you take div of that section on the model, again, you pick up zeros and poles, and that collection, the multiplicities of zeros and poles of omega, give you the sequence of chip firings which take the reduction of k to the dual graph to the canonical divisor. So the canonical divisor on the dual graph is not necessarily the reduction of some canonical divisor globally, but it's equivalent. And this business, this problem before of zeros and poles on this model becomes a solution. It tells you how to make k equivalent to k gamma. All right, so that's it. Thank you.
Any questions for David?
Right behind you.
Always behind me.
You were saying you were doing all this for the case that you just had individual components intersecting each other. What if you have like a component that's got a node or a cusp or something? Does everything blow up, or are you?
Great. So there are details. One detail is not every reduction is semi-stable. So at least for the Chabauty application, for this 2R, the rest of the bound, how to say, in this setup, so we do this setup with whatever model we start with, and we set up this Chabauty divisor. And then we forget about the Chabauty setup. We now just have some divisor that we're trying to bound the degree of. And if we base extend to some field where we attain semi-stable reduction, then if we bound the degree of that divisor there, we're just as happy. So, and then of course, you can even bound the degree over which you attain semi-stable reduction. Okay, on the other hand, what I'll talk about next time is it is really a problem that in this Lorenzini-Tucker and in our theorem, you're working over the FQ points of the regular model. You'd really like to work with a stable model. And in that case, I think what you were hinting at is if you take a model and inflate the model at a point, the effect of this is just you insert a P1 which intersects here and intersects here. The effect of that on the dual graph is you're just subdividing. And so what we do in the continuous case is instead of having to worry about the combinatorics of how all of this changes when you subdivide, you may as well work with the metric graph in the Berkovich space. And it's just much cleaner. Or rather, we couldn't do it without using the continuous version.
Okay, let's thank David again. And we'll take a short 10-minute break.
I touched my nose and touched these a few times, so I'm just going to take these.